exponential growth and decay. So we're still working with our exponents, and we're going to be looking at a couple of formulas that deal with growth and decay. So we've got two formulas very similar to each other. The only difference is whether we're talking about growth, where we're adding something, or decay, where we're subtracting something. So we have these two formulas here, y equals a, and then in parentheses 1 plus r, close parentheses, to the power of t, or y equals a 1 minus r, with close parentheses, to the power of t. So our growth formula is our addition, and our decay formula is our subtraction. So which one you use depends on what's happening in your particular situation. And we'll be working with word problems for these ones. What do each of these variables represent? So y is your final amount, the amount that at the end of the time period that you're talking about, that's how much you have. A is the initial amount, the amount that you start with. T is the time, so how much time is passing. And R is the rate of change. We need to make sure we write the rate. Rate will be a percent. We need to write that as a decimal, so we need to change our percent to a decimal. All right, let's apply these. So the population of the United States has been increasing at an average rate of 91/100% per year. If the population was about 303,146,000 in 2008, predict the population in 2012. So we're going to pull out the different pieces that we need for our formula here. Since we're talking about a population that's increasing, we'll use our growth formula. So we'll use this first formula. Again, the only difference is that it has plus in the middle. A, our initial amount, is our 303 million amount. T, we're going to do a time of 4 years to get from 2008 to 2012. And our rate is that 91/100%, but we want to write that as a decimal, so we're going to move that decimal place over 2 places to the left, and we'll call that 0.0091. That's what we use in our formula. So we're going to plug those values into our formula here, and we're going to simplify what's in the parentheses. We need to do that to the 4th power. So at this point, I want you to grab your calculator if you don't already have it, please. Hopefully you have one at home. If you're watching this, you're probably on your computer. So if you don't have one handy, you can grab the one that's on your computer and use that step by step. But what I want to notice here is that these numbers are going to get really long, and it's going to be complicated to try to consistently write down each step as we go. So at some point, you're just going to have to shove everything in your computer and in your calculator and see what you get for an answer. However, I want you to be careful about your order of operations, and I want you to be careful about how you put each thing into your calculator. Now, the reason I don't really want you to write it, kind of do each step here as we go, is because your tendency will be to round. And especially when we work with these really large numbers and with our exponents, which change really quickly, the sooner we start to round our numbers, the farther off our final answer will actually be from what it should be. So we really don't want to round, and the easiest way to do that is to just leave our numbers in our calculator. So I'm going to start here with my 1.0091, 1.0091. Now, to do a 4th power on my calculator, I have this, I don't know, can you see it? It's a little caret key there. I'm going to use that caret to the 4th power. I'm going to press equal. It's going to tell me what that exponent, what that power is. I'm going to leave that on my calculator. And then I'm just going to do times 303,146,000, and that gives me my 314 million number that I came up with here. So I'm hoping that you can take a second, pause the video, try this on your calculator, and see if you're getting that particular number there. Again, be careful that you don't multiply these bases first and then work with the exponent. It's always parentheses exponents first. So here we have parentheses with our exponent. We have to do that first. So our final answer here is about 314,332,051 people for our final number. Again, this is going to be some calculator practice here. All right, second problem we're going to do. Mr. Gossel is a machinist. He bought some new machinery for about $125,000. He wants to calculate the value of the machinery over the next 10 years for tax purposes. If the machinery depreciates at the rate of 15% per year, what is the value of the machinery to the nearest $100 at the end of 10 years? So depreciates, you're going to start to see this word depreciates, it decreases. So the amount of money that this machinery is worth as time passes goes down, it decreases. So this is going to be our exponential decay. You might see the word appreciates, which means it increases. So if the value of something appreciates, it increases. If the value of something depreciates, it decreases. So this will be exponential decay. Again, this is my starting amount, 125,000. We're going to do a time of 10 years here. And the rate that this is depreciating at is 15%. We're going to use that as a decimal, 0.15. So here's my 0.15 that I put in here. So again, what I would like you to do is pause the video, grab your calculator, plug this in, and see if you're getting $24,600. That's what you should get. I'm going to take a second here and double check my math here. 0.85 times to the 10th power. I'm going to leave that on my calculator, and then I'm going to do times 125,000 and 24,600. I got about 609, but they said to round to the nearest hundredth. So that's what I did. I got 24,609.30054 is what my calculator says. So if that's what you got, you're looking good. So that is our exponential growth and decay. Which formula you use depends on whether in that situation we have something that's increasing, we'll use growth, our addition, or it's decreasing, we use the decay, we'll use our subtraction.